People, alright, this is the final video for the 3D geometry related rates problem. Let's go ahead and jump right in. A spherical iron ball is coated with a layer of ice of uniform thickness. If the ice melts at a rate of 8 milliliters per minute, how fast is the outer surface area of the ice decreasing when the outer diameter, ball plus ice, is 20 centimeters? Now, why there's an iron ball inside the ice and why that's necessary to tell us, I have no idea. Why it couldn't just be a spherical piece of ice, whatever. But one thing that needs to be noted here, I don't know if you knew this, you probably do because you're probably taking physics and you remember all this stuff. It's been forever since I've dealt with milliliters and how those relate to centimeters cubed and stuff like that. But I actually had to look it up. I had a hunch, but, you know, it's been so long. So, what we're given here, is our dV/dt, right? If the ice is melting, the volume is changing, and of course it's melting, so it's negative, at 8 milliliters per minute. But that just means that it's 8 centimeters cubed per minute. Now, why you would actually put milliliters there, for the people who don't remember, instead of just calling it centimeters cubed, I have no idea. But since I didn't write this question, you can't blame me. So, the question is, how fast is the outer surface area changing? So, dA dt. And oh my gosh, we have another one where we're given dV/dt, and asked for dA dt, and that means that, just like the last one, we can do it in two different ways. I think I proved that actually creating a formula for area in terms of volume, probably not the way to go, okay? But we do know how to do it the other way. Now, how fast is the outer surface area of the ice decreasing when the outer diameter is 20 centimeters, so the outer radius is 10 centimeters. Okay, well, let's go ahead and find let's do our volume formula in order to find our dr dt, because that's going to be necessary for the area. So volume is 4/3 pi r cubed. Area is 4 pi r squared. My dV/dt is 4 pi r squared dr dt. And when I go ahead and plug in, I'm going to get negative 8 centimeters cubed per minute is equal to 4 pi times 10 centimeters squared times dr dt. And therefore, dr dt is equal to negative 8 centimeters cubed per minute, all of that over 4 pi times 100 centimeters squared. Well, the centimeters squared obviously go bye-bye with 2 out of the 3 of the centimeters up here. The 8 can cancel with the 4 and leave a negative 2, but it can also take a 2 from here and turn it into negative 1. And therefore, what I have here is I have negative 1 over 50 pi centimeters per minute. Okay, I sort of crowded myself out a little right here. Let's hope that doesn't come back to bite me. So when I have dA dt, I know that that's going to be 8 pi r times dr dt. Now, I had a little bit of a heads up because I just did a problem like this. So I knew I had to go fetch my dr dt, but even if I didn't, I should know from right here that I don't have dr dt. And therefore, if I need dr dt, it's either given to me explicitly or it's implied from the information that's been given. I went ahead and found it ahead of time because, you know, I, again, saw the problem from the last one. It's a similar problem. And I basically plug in 10 right here, and this becomes negative 1 over 50 pi centimeters per minute. Now, centimeters and centimeters, when I actually multiply this all out, it's going to be centimeters squared per minute. That actually is what it should be. Okay, and so the 10 right here cancels with the 10 inside of here, leaving a 5. The pi's will, of course, cancel out, and what I'm left with is negative 8/5 centimeters squared per minute. And that is our final answer, okay? I'm not going to go through the other way to do this one. That just sounds like torture to me. And this is easy enough. I mean, each one of these is a related rate problem in its own right, but both of them are simply 4 steps, so not overly burdensome. All right, let's do another sand pile problem. Yay! Sand is being poured onto the ground, forming a conical pile whose height is equals 1/4 of the diameter of the base. Okay? And we're going to go ahead and draw ourselves a nice little conical pile, not to scale. You know, oh, that was horrible. Again, I need to really work on that. And we have a radius. So we have basically our height, we have our radius, and we know that the height equals 1/4 of the diameter. So if the height equals 1/4 of the diameter, it equals 1/4 of twice the radius, or just 1/2 of the radius. Okay, that's going to be helpful. Now let's go ahead and keep reading. If the sand is falling at a rate of 20 cubic centimeters per second, well, we can basically discern from the units that that is a dV dt. Now, of course, unlike the conical reservoir that's tipped upside down where water is draining out, and therefore dV dt is negative, here sand is being poured onto the onto the pile, and therefore it is positive 20 cubic centimeters per second. The question I am being asked is, if the sand is falling at a rate, okay, how fast is the height of the sand pile increasing? So what is dH dt? Now, what I need to know now, sorry, I was turning off the Wi-Fi so we don't get interrupted by a phone call coming through my computer. If the sand is falling, how fast is the height of the pile when the height is 3 centimeters? Okay, so the conditional is h is equal to 3 centimeters. Now, thankfully, both the volume and the height are in terms of centimeters. I don't have to change things, okay? Now, if I'm looking here, I know that the volume of this is a volume of a cone is pi over 3 r squared h. Again, 3 variables. But you have to remember that this information was not given to us just because. It wasn't sort of just for our information. It's not wasted information. We've seen that before. It usually doesn't happen. That is going to help us turn this formula of 3 variables into something in terms of 2 variables. Now, the question is, which one do I want to plug in for what? Well, I've given a conditional in terms of h. I'm asked a question in terms of h. I think I need to get rid of the r. So I need to figure out what r is equal to. Well, h is equal to 1/2 r. r is equal to 2h. So I'm going to take this bad boy, and I'm going to plop it down right inside of there. And it's going to be 4h squared. So that becomes 4 pi over 3h cubed when I plug it in and simplify. Now, I have a pretty straightforward formula of 2 unknowns, and therefore I can differentiate because that unknown that's left over here matches the conditional and the dH dt that I'm being asked for. So this becomes 4 pi h squared dH dt. Now, of course, you would know if you substituted the wrong way, because you would get to here and you would have r's, you would have an r and an r dr dt, and you wouldn't have the information necessary to plug in. And you would just back up and do it the other way, right? So I have 4 pi, and then h squared is 3 centimeters squared. And then dH dt, well, I'm looking for dH dt. It's actually the dV dt that I needed to plug in for, times dH dt. and therefore dH dt is equal to, well, this divided by that, right? Because the other side is 20 centimeters cubed per second, and then it needs to be divided by, well, that's 9 centimeters squared, so that's 36 pi centimeters squared. Well, the centimeters squared can be canceled with 2 of the centimeters from that right there. The 20 and the 36 obviously both have 4s as a factor. So that's going to be 5, that's going to be 9, and what I have is 5 over 9 pi centimeters per second. And if you want a decimal approximation, you can go ahead and plug it into your calculator and get it. But that's roughly, let's see, if pi is 3.14, 9 times 3.14 is 28, 29, something like that. So 5 over, it's going to be a little larger than 5 over 30, which is 1/6. So that's the ballpark that you're playing in. Okay. And then, of course, you would write me a sentence explaining what that numerical answer means. All right, let's move on to the next one. A water trough with vertical ends in the form of isosceles trapezoids has dimensions as shown in the figure. If water is pumped in at a constant rate of 1/2 meters cubed per second, how fast is the level of the water rising when the water is 1/4 of a meter deep? Okay, so my given is if the water is pumped in at a constant rate, so dV dt, it's going to be positive because the water is being pumped in, right, because it's increasing the volume, 1/2 meters cubed per second. My question, we'll go ahead and abbreviate it as Q since I don't want to run into my little figure right here. The question is, how fast is the level of the water rising? Well, the level of the water is going to be, let's call it H, height, right? dH dt is equal to, okay, question mark. Now the conditional information is when the water is 1/4 of a meter deep. So when H is equal to 1/4 meters. Now, I'm really interested in this. I'm really interested in the trapezoid at the end, right? The length is never going to change, but the shape, the size of the trapezoid is going to change. So let's draw a trapezoid over here and focus on that. Okay. And it won't be to scale, but now this right here is 1 meter. This right here is 2 meters. And the water is going to be somewhere in here. Now, this right here is 1 meter. The question is, how am I going to get a formula that actually represents the area like this? Okay. Well, we know that the area of a trapezoid is going to be base 1 plus base 2 over 2 times the height. Now, we know that that the first base is going to be 1 meter. And we know the second base is going to be somewhere between 1 and 2. We just don't know. Well, what you need to remember is that an isosceles trapezoid can be divided up like that. Okay. Now, an isosceles trapezoid where it's 1 and 2 is actually, yeah, I'll go ahead and redraw it. It's going to have 45, 45, 90 right triangles. And so actually I'll just sort of extend these out a little bit instead of totally redrawing it. Okay. Because if this right here is also 1 meter, and this is isosceles, then this over here, it's actually not 45, 45, 90, but very predictable. This right here is 1/2 a meter, and this right here is 1/2 a meter. So if the height is 1, and this is 1/2, okay? Then basically this small triangle down here will have the same proportions, right? And so you're really dealing with similar triangles sort of contained within this. And you can actually carve this up into basically the rectangle right here plus the two triangles. But let's go ahead and deal with the two triangles right now. Okay. Basically what needs to happen is you need to figure out, you know that basically what's going to happen is the volume of this thing is going to be base 1 plus the base 2, right? We'll call it B since we already know the value of base 1, over 2 times H times 4. Because 4 is the length, right? That's what it's going to take this area and turn it into a volume. Well, this obviously can cancel out with one of those, and I'm going to get 2H times B plus 1. Now the question is, what is the relationship between H and B? I need to change B into an expression in terms of H, because as I did in the last one, I have my question in terms of H and I have my conditional in terms of H. And I'm going to use these triangles to do it. Now this second base is going to be 1 plus those two little pieces right here. Well, if the original triangle is going to be, basically has the proportions of 1 to 1/2, then whatever H is, right, then base is 1, is basically, this is 1/2 of that. But since there's two of them, basically every time you have an H, you also have a B. And so what you have here in terms of the proportion is you have every time you have H, we'll call this X, okay? You know that you have the height of 1, right, is to H. So 1 is to 1/2 as H is to X. And you know that that's 2H over X. And so 2X is equal to H. Or sorry, I got that. No, that's right. And so H is equal to 2X because X is equal to 1/2 of H. But here's the thing, my base over here, right? My base is equal to 1 plus 2X. So it's going to be B is equal to 1 plus H. That is my conversion. I know it's a little bit convoluted because you're having to deal with the triangles within the isosceles trapezoid. And there might be a different way to do it, but this is the way that I saw it. So we're going to take that and put it right in here, which makes this 2H, H plus 2, which becomes 2H squared plus 4H. Now, from here, I can go ahead and differentiate, and I get 4H dH dt plus 4 dH dt. So let's just go ahead and factor out the dH dt. And my dV dt is 1/2 meters cubed per second. My 4H is 4 times 1/4 plus 4 times dH dt. Now this is 5. And therefore dH dt is 1/2. By the way, this needs to be, meters. Basically what happens is I need the 1/2. I'm going to be dividing it by 5, and that's going to give me 1/10. And I lost units in there a little somewhere because I was more interested in figuring out the formula and how to do the substitution. But that winds up being 1/10. But remember that this, so it's 1/10. The height is increasing at a rate of 1/10 meters per second? Yeah, per second. Yay. Okay, now that one was a tough one, but I wanted to end with one that was a little bit tough, and it wasn't really tough like once you got, the calculus wasn't tough. It was the figuring out how to substitute in and get an equation of 2 variables instead of an equation of 3 variables, so that you could then differentiate and basically not have to go searching for any more things. You might not have thought, you might be thinking to yourself, well, I would never be able to do that. Well, you know, once you've seen it a couple times, yeah, you will, okay? I'm going to go ahead and call a close to the 3D geometry related rate problems. I'm going to go ahead and get started on the videos for the trig-based ones. But as always, if you have any questions, please do shoot me an email. Bye.